and Chief of Products, excuse me, and Innovation at Nanoramic Laboratories. I'm going to be talking about high power innovation, the methodology behind product development and commercialization. So maybe a little bit more back to earth, but still probably a little bit out there. So John, thanks for being with us today, and we're going to let you take over.
Great, thanks a lot for having me. I'm John Cooley, founder and chief of products and innovation at Nanoramic Laboratories in Boston. I'll be kind of geeking out today a little bit on our methodologies and also lessons learned in product development, commercializing technology. We have a product innovation business model, so we focus on the process of product development quite a lot. And so I'll get into some of that in some detail here. So today I'll go through some brief company history and context for the material. So I'll go through some brief company history and context for the material. Then I'll discuss product development in 3 broad topics, and I'll try to tie in some stories along the way. Start my timer here. So just first, a little bit about me. I grew up in Baltimore, Maryland, and moved to the Boston area in 2001. I live in Concord, Mass. with my wife and 2 kids, shown here. I spent 10 years at MIT, earning 5 technical degrees from the electrical engineering department and physics department, including the PhD. In 2009, I co-founded Nanoramic Laboratories with a $5 million grant that we won writing out of the basement of MIT. I spent the first 5 or 6 years directing frontline product development in sophisticated electronic and energy storage-based hardware systems at Nanoramic. And today I'm Chief of Products and Innovation and a board member. So the company began in 2009. We spent the first 5 or 6 years on parallel tracks with advanced R&D and energy storage technology, and also commercializing and deploying advanced energy storage and power systems in our alpha market. The alpha market was oil and gas, and that collapsed in 2015 when we repositioned to focus more on energy storage and advanced materials. And we doubled down on our core competencies in product development and built out an innovation business model and grew that to include 3 business lines. Today, we are delivering on a longer narrative arc to start in oil and gas and ultimately deliver cutting edge technology into clean energy. One of the things that we noticed when we started out were all the cautionary tales in new clean energy technology startups making breakthroughs on advanced technology and then immediately seeking massive capital investment to scale up manufacturing. Time and again, we saw this model fail. Technological breakthroughs and high volume manufacturing require completely different skill sets. Even for a well-heeled, established high volume manufacturing business with lots of cash, accomplishing both tasks is risky and usually unsuccessful. So to come from the other direction, to begin with limited funding, develop a breakthrough technology, and then establish high volume manufacturing seemed less and less rational as we watched these stories unfold. So instead, we eventually built into our own DNA a product development focus and manufacturing partnership mindset. And today, this has become firmly rooted in our strategy and culture as a product innovation and licensing business model. This model affords us the opportunity to access multiple markets, to exploit technology capabilities, and to focus resources on product development, which is a very different skill set from high volume manufacturing, as I mentioned. The idea is to repeat this cycle over and over again and to layer on product successes and of course the revenue they generate, and to do it without massive infrastructure or the capital investment that goes along with it. Some of the lessons learned in the stories and the topics that follow have become fundamental to this model. And to this point, this model has helped us rapidly grow 3 business lines, each with their own success stories. The common theme among these business lines is our core competency in advanced materials and product development. And with each cycle of new development, our market opportunities have grown by several factors. We've been able to do this with a lean staff and infrastructure. And our flagship technology is a descendant of where we started, an advanced energy storage electrode. This is the one at the top there in the picture, the slide. And it's an elegant solution to reduce costs and improve performance of the most costly components in a lithium-ion battery, which is the electrode. With the rapid growth in the electric vehicle market, This and our lean business model positions us well to make an outsized impact in clean energy. And today we're able to clearly say that we've completed our narrative arc to begin in oil and gas and to finally commercialize breakthrough technology for clean energy. So I'll talk about product development in 3 topics, and I'll try to tie in at least one story for each one. The first one is kind of fun. I call it groundhogs and oil rigs. So in the first 5 years of the company, we decided we needed a low volume, high price point market to support the company while we arranged our technology to enter clean tech markets later on. And that alpha market, as I mentioned earlier, was oil and gas drilling. And we designed our way into it by inventing the world's only high temperature supercapacitor. It's a certain type of rechargeable energy storage device. This is still to our knowledge the world's only high temperature rechargeable energy storage technology that's commercialized. It operates up to 150 degrees Celsius, and it's really intended for oil and gas drilling, but it has other markets as well. I led the team that did that, and we also designed very sophisticated harsh environment and space constrained electronic systems around it. Here are some pictures just to get an idea. On the left are some electronics that we designed. They're very compact and high power, and they're also designed to operate at high temperatures and high shock and vibration conditions. They look kind of like this photo on the left. And they went into long cylindrical systems that we designed, like the photo next to it. The next photo there is a system fully assembled in a pressure barrel that's in a hut, actually, by an oil rig in Texas. And we deployed these systems in situations like this one on the right, so quite dirty and chaotic. In 2014, we deployed in the field, kind of in a rush. We succeeded for the most part, but we did find ourselves making basic design changes on the fly. For instance, we never connected both of the 2 battery packs in the system to the DC bus in the design. That limited the power of the system. So we had to hack a connection on the oil rig floor with soldering irons and wire clippers. And this kind of experience, that was just sort of one example, but that kind of experience led us to understand the value of qualification, really to simulate as best you can in the lab the real world load conditions as a method for qualifying your design before it goes to the field. The product we deployed in the oil well also had a component to it on the surface. So the downhole, so to speak, portion was a high power data transmitter. And on the surface, we had a very sensitive data receiver. And that receiver required us to walk very long cables far out into the pastures where the oil fields were. In these photos, you can see in the foreground on the left are cabling. Here, kind of in the foreground, the ground, so the gray wire. In the background, some oil rig equipment. You can see some cattle and oil rigs in the background to get a sense of the situation on the right. A few times we lost signal, and in our troubleshooting, we'd had to walk the lines out into the pastures. And it turns out we saw a lot of this. The picture on the left is a Texas groundhog. And several times we found that these guys had chewed through the receiver cables way out in the pasture, and we figured they didn't much appreciate us treading on their usually quiet territory. And we called this groundhog interference. It was common enough that we had a name for it. And we learned that there are some things you can't simulate in the lab. So this led to a permanent stage of our process, field testing, or in some industries, we call this validation, especially the medical device industry, we call it validation. By 2014 or so, we had developed a relatively conventional stage gate process for product development that captured a lot of these aspects. And you can see qualification and validation there. You'll notice the sequential nature of this process, and we'll come back to that later. Another important lesson that we learned during this time was ultimately about what would become our long-term business model and strategy. And as a small company from Boston, we ended up vertically integrating as far as providing field service. When we reflected on our business in 2016 after the collapse in the oil and gas market, we thought it had just been bad strategy. But today, having succeeded in licensing the core technology to an oil and gas manufacturer, we now recognize what we did as control of the value chain. So we saw that it was difficult to convince the end customers just to buy the high temperature supercaps we had developed. So we designed it into our own systems there in the middle. Then we saw that it was difficult to train someone else to effectively deploy our systems. So we built our own field service organization. And that's actually me on an oil rig deploying our products in the field. We eventually became designed into the flagship product of one of the 4 big drilling service providers in the world. And with that, we began to threaten the market share of our competitors. And that gave us leverage to strike deals with our customers and competing manufacturers. And ultimately, we succeeded in our goal of licensing out the core technology because we demonstrated its commercial viability all the way to the end customer. We controlled the value chain and we threatened market share. And today we've moved on to products in other markets and clean tech while we enjoy royalties from this first product without bearing the burden of high cost manufacturing and sales channels to support it. So in summary, to license this, we first did all of this. This is just a basic picture of the value chain in oil and gas drilling. And that strategy is a permanent part of our licensing business model today. Control the value chain, threaten market share. Or in other words, in order to license, you must act as if you will not license. All right, so the lessons learned here are as follows. There are things that you cannot skip to make a hardware product successful. Among those steps are qualification or internal proof that the product meets the requirements, and field testing or validation or proof that it does what it needs to do at the end application. The other lesson we learned here was to control the value chain and threaten market share to be successful with new product introduction and especially licensing technology to manufacturing partners. In particular, we like to say, to license, you must act as if you will not license. All right, so my second story is called Not Agile. And this story starts with failures in a product that we were developing in late 2017. The stage gate process on the left here creates checks and milestones on product development. This is a picture of the process I showed you previously. It serves to provide deadlines and deliverables and to define the nature of the work that should be happening at any moment in the process. You're all probably familiar with the Gantt charts and waterfall planning shown below. These methods work in some contexts, but not all. They have key drawbacks. In particular, it's easy to accumulate delays in the process. And because of this sequential nature, there's a lot of risk that new information discovered at the end of the process can require it to iterate all the way back to the beginning. On the right is what's widely considered the opposite end of the spectrum in terms of agility. This is the Scrum framework. It was developed in the context of software product development, and it's intended to build in-market feedback to the development process, and it's designed to create shorter-term goals that focus the team on achievable results. It's supposed to make product development easier to predict and more adaptable to market demands, and it works well for software product development, but we learned that it has some limitations for other types of products. We spent the first 5 years operating something like the process on the left. In 2017, we were fed up with the limitations of that and threw it out, and we adopted software Scrum on the right, and then we learned some valuable lessons. When we came to the end of 2017, we finally got a large sample of these new products that we were developing under test, and witnessed to our surprise widespread failures. We came back to the office after a holiday of stressing and got to the bottom of it. By the way, this was a new product that we had started developing in 2017. It's not sort of the older products that I had just described at the beginning of the presentation. So after some questioning, I found that we had been moving much more slowly than anyone had thought on this new product. I asked, why are we moving so slowly? And the answer was to the effect of, well, our Scrum sprints are about 2 weeks long, and we spend one of those days planning and one of those days retrospecting, then another one grooming. And when we lock in the sprint, and this is all, by the way, Scrum language, nobody feels that they can change what they're doing until the next sprint. So if we learn something in the lab on day 3, we have to wait until day 15 to do anything about it. This was anything but agile. And after some more debate and reflection, what we learned is that especially for hardware product development, and even more so if there's an empirical or experimental aspect to it, a literal interpretation of software Scrum is more likely to mask your slowness than it is to speed up your development. So instead, we looked at both ends of the sort of not agile to agile spectrum and chose the aspects from each that served our needs best. And after weeks of debate and brainstorming, we found that these were the elements. Set the objective, the requirements and the releases, and provide a definition of done that reveals the critical path. Create practical milestones and methods for gathering customer feedback from deliverables, for instance, documentation or shippable hardware. Don't overburden the development team, but don't wait until the end either to get feedback. Create the interfaces, and this means creating interfaces between stakeholders, both internal and external. Set a schedule for that and make sure that you get feedback early and often. And then allow a balance between structure and agility. So define a framework and a language, then let the team adapt to it with the reality on the ground. Here's the core process we came up with as a team. You can recognize some of those aspects there, and a basic visualization of the day-to-day work. At a high level, we created a language, a framework, and a process that we use to keep ourselves honest, to know when to say no, to know when we are on or off critical path, and then we allow adaptations to suit the reality on the ground. So it's a process, but we're really not slaves to it either. Zooming out from the core process, we developed a full picture of the product lifecycle shown here. This has become our innovation map or product development map, and it spans the full cycle life of each of our products. And you can recognize the core product development process at its center. This map is useful as a mental model. We actually print it and post it in our common areas and refer to it in our strategy discussions. You can do nice things with it, like overlay the relative activity of different stakeholders throughout the life cycle of the product. These are just some examples: manufacturing, business development, corporate development, just to give you a sense of how you can use it. So lessons learned: acknowledge that the right process for your product might not be off the shelf. Look at what actually works and what doesn't for your product. Feel free to take aspects of several processes and mix them together. Define the framework in a common language to provide solid footing for the team, and then let them adapt and innovate. There's a lot more to that, but a little limited on time. All right. So the last topic that I'm going to talk about is what I kind of characterize as our desire to design something to work the first time that you build it. So I come from an electrical engineering and circuit design subculture where you're kind of shamed if your product doesn't work as expected the first time you build it. That means that you didn't think of everything. But not all technology is so well understood that you can expect that level of perfection at the first prototype. Depending on the technology, you may have to recognize that your product development process is highly empirical or experimental. In other words, you have to prototype and test to understand things about the system. This is a critical distinction to make depending on the type of products or subsystems that you're developing. So we've come to studying how we can optimize the throughput of our empirical product development processes. And the main theme here is really a basic respect for and effective use of the scientific method. When we say throughput of our empirical product development process, we're really talking about the rate at which we acquire conclusive answers to questions. And secondarily, the rate at which we reveal new questions, or the rate at which we resolve the issue of we don't know what we don't know. One thing that we notice is that sequencing poorly designed experiments is the kiss of death for empirical product development. What tends to happen is something like this. We observe an effect or a defect in a prototype, then jump to an assumption about what's causing it. And in the language of the scientific method, an assumption that a prediction from a hypothesis will be proven true clouds our judgment and narrows our focus from other viable hypotheses. Why test something else if we already know what it is? The truth is, it's almost never that first thing, but you build it, you test it, and wait, sometimes a long time, and only to find out that you jump to conclusions. So we want to get better at that. By reinforcing the scientific method in place of this kind of behavior, we observe, hypothesize, predict, and then test with conclusive results. The rate that we obtain conclusive results is in fact the throughput of our empirical product development process, So we want to do everything we can to increase the conclusiveness and efficiency with which we come to those results. And to shortcut the original problem I described, the narrow focus on one hypothesis assumed to be true, we must advance multiple hypotheses simultaneously. And even for one hypothesis, we must also test the effect of multiple inputs on the output that we're studying. So we must have a framework for parallel tests, and this is really based on design of experiment, which is a whole subject that I won't get into in depth here. Then we group those tests into investigations, and each one corresponding to a study of the effects of multiple inputs on a single output. And once we do that, we can pursue investigations in parallel, adding a second layer of parallelization to our experimental workflow. Then we allow those investigations to interact. For example, observations and conclusions from one investigation can inform a new investigation or a design decision or both. And once we've reasonably answered all questions and make all of our design decisions, sorry, I skipped ahead. So stepping back, we set out to make design decisions with an experimental workflow so that we can release a design. We may have parallel sets of investigations, all informing design decisions or follow-on investigations. And once we've reasonably answered all questions and make all of our design decisions, we can release that design. These periods of investigation culminating in releases can follow a pattern that aligns with our business objectives, and you can recognize this graphic as the core process in our innovation map. The idea here, going back to the prior lessons learned, set the objective and the deliverables, let the team innovate. The periods of work seem chaotic, but so long as they have a sight line on the critical path, the chaos boils down to a releasable product. So to summarize this last story and the lessons learned, the methodologies in your product development process should reflect the nature of the technology. How empirical or experimental is the work that's needed to develop the product? For empirical product development, a disciplined respect for the scientific method is essential. The throughput of empirical product development is the rate at which we obtain conclusive results, and empirical product development can be accelerated by layers of parallelization and good, thoughtful test planning. So I hope you found that interesting, and please feel free to reach out with any questions. Thank you.
Awesome. Thanks, John. That's a great overview.